Hi, everybody. I'd like to welcome researcher Emma Maurizio, who is going to tell us all about the giraffe rocket mission. Over to you, Emma.
Thank you. All right, yeah, my name is Emma Maurizio. I am a PhD candidate at the University of Maryland, but I do most of my work at NASA Goddard Space Flight Center, including the giraffe mission, which launched earlier this year. And I am presenting this work on behalf of our team. And the PI is Robert Michel, and all of the NASA people are unfortunately furloughed right now. So I hope I do the mission justice. So this is Giraffe. We launched two rockets. Oh, let me see if I can advance my slides. We launched two rockets into the Aurora earlier this year. This was in February of 2025. We launched from Poker Flat, Alaska, which is near Fairbanks, and we launched north into remote Alaska through the Aurora, through these active auroral arcs. This mission is GIRAFFE. It stands for Ground Imaging to Rocket Investigations of Auroral Fast Features. And I'll talk about those fast features specifically that we're looking at in the next few slides. But here I just wanted to show the part of Alaska that we flew the rocket through. We have lots of ground-based imagers throughout the rocket's flight, but mainly at Venati in Venati, Alaska, which is near the peak of the rocket's flight, so near apogee. And I just have an image on the right here of the Aurora and our mission logo. But the main goal of this mission is to understand the fundamental processes that create these fast-changing auroral features that I'll talk about in a minute. And by sending these two rockets directly through these features, we can better understand the types of the aurora that we're talking about here. These two types of aurora are flickering aurora and fast pulsating aurora. And I'll talk about those right now. So first we have the pulsating aurora, or the fast pulsating aurora, which is what Giraffe targeted. This is aurora that flashes on and off, and it's believed to be caused by electrons bouncing between Earth's poles, and so jumping along those magnetic field lines and then brightening the ionosphere and then dimming and then brightening and then dimming. Pulsating aurora can happen over the course of like tens of seconds, so like 10 to 40 seconds, but specifically the fast pulsating aurora can happen up to a few times per second, which is what Giraffe is targeting with our myriad of instruments. So this video on the right here is a little bit sped up, but you can see the patches coming in and out. So there's these main auroral structures that move across the sky that everyone is more familiar with. And then there's these patches that seem to stay in the same spatial location and then just dim and then brighten and then dim and then brighten. And that's what we're looking at. You can see some of those patches in the center of the field over on the right as well. And then, so we have two rockets for Giraffe. This is what the first rocket was targeting. And then we launched another rocket when we wanted to see the other auroral feature, which is flickering aurora. So the difference between flickering and fast pulsating is the frequency. So flickering aurora flashes on and off up to 15 times per second. So it can look a little bit like TV flickering or TV static. As you can see in the middle of the image on the right, it sort of just looks like it's flashing on and off really fast. And this video is in real time, so you can see just how fast that flickering it is. And these events can last for a few seconds during substorms and sort of active events, but we've actually found that they can last much, excuse me. They can last much longer during quieter early evening auroral events. And that's when we can have enough time to actually shoot a rocket through them if we're able to catch it. So these are the two types of aurora that the rocket is targeting. But what we really need to do is have the instrument capabilities to be able to understand what's going on in these types of aurora, which is something that we were able to do with the suite of instruments that we have on these rockets. So I wanted to talk about those instruments a little bit more. So first, APES, which is the Acute Precipitating Electron Spectrometer. You'll notice a lot of these things are named after animals. But APES is an instrument that goes on or went on the nose cone underneath the nose cone of these rockets. It has a single look direction, but it has really high speed, it collects really high speed electron spectra. And we do that by having a magnet inside of the instrument, so at the bottom of the instrument here, and then the aperture is on the other side that you can't see from this image. But the magnet bends the electrons toward the detector. And by doing that, we can split up the energy of the electrons to get a full electron spectra every millisecond. So that's a super high speed way of collecting electron energy spectra. And this is one of the ways that we're able to capture these super high speed auroral events like the flickering and the fast pulsating aurora. So this is flown on a few other missions. It flew on Greece, which is a rocket by whose PI is Marilius Mara in 2014. It's flown on a bunch of rockets since then, and it's a really great instrument that's given us a lot of new insights into these auroral features by using sounding rockets. Next, we have CHIMPS, which is the capped hemispherical instrument measuring particle spectra. I'll double check if I got that right. But this is a really high resolution pitch angle measuring instrument. So it has a 200-degree field of view, as you can see this top part here, where all of the electrons can enter. And it has a bunch of anodes so that we can have high resolution in pitch angles up to 3 degrees of resolution. And using this instrument and an electrostatic analyzer, which sweeps through voltages up and down, we can also get really good time resolution readout with this instrument. Not as good as using magnets, but still able to capture these fast features. So this is a new instrument that we were testing out for these rockets. And then we have APES 360, which is acute precipitating electron spectrometer, 360 degrees, which is a high-speed electron spectra instrument that has 16 different look directions. So instead of having one magnet where we collect an electron energy spectrum with the magnet every millisecond, we have 16 of these magnets that are all in a circle on the top of this instrument here. And we're able to collect these energy spectra from all different locations. We're able to capture the downgoing electrons, the upgoing electrons at all different pitch angles. And we just have it on a scale here to show you how light and small this is and how useful it would be for other missions. So we had a bunch of really great instruments. And so this is really the first time we're able to capture with these sounding rocket missions, these really fast changing auroral features with these really high fidelity instruments. And then I also just wanted to put a spotlight on the ground-based observations that we do as well. So this is just an image of the roof of the Science Center at Poker Flat Research Range in Alaska. So they have all of these domes where we can put all of our different instruments. We have all sky cameras, we have narrow field cameras, we have really high speed, like collecting images super, super fast so that we can see all of these different features. We also have different wavelengths, so observing just red line, green line, and blue lines rather than all color images so that we can really have a mission that observes the electrons in situ, the particles in situ in the mission, as well as what it looks like from the ground so that we can compare these and put it all together. I just wanted to give a quick look at the rockets all put together. So on the left here, these are just the payload part of the rocket. So these are both Giraffe rockets when they finally made it to Alaska and we put everything together. Underneath the nose cone there are the two APES instruments. And then in the main body of the payload, we have the other instruments that I just showed. So CHIMPS and APES 360 actually came out on booms, which you can see in the picture on the right here. That green pole deploys outward. And so you can have the instruments be a little bit separated from the rocket, be able to see for APES 360 all 360-degree field of view. And then for CHIMPS, that 200-degree field of view, able to look at the electrons in that sense. And then after putting all of these instruments together, integrating them onto the rockets, being in Alaska for a very long time, we launched both of these Giraffe rockets. So we launched the first one on February, I believe this is February 2nd, and then the second one was February 9th of 2025. And you can see here, this is our mission control center. So on the left, this smaller clock is the T-minus countdown clock. So this is a minute before launch. And then we have here our UTC clock. We have all of our Aurora monitoring windows up. So we're monitoring what the Aurora looks like, waiting for the right conditions. We have the magnetospheric conditions pulled up, the magnetic fields in all different directions. And then we have some ground-based magnetometers up at the very top here that we're also looking at. So we're trying to find the best conditions, predicting what the aurora is going to do in 5 to 10 minutes when the rocket's going to be at its apogee. So it's a very delicate balance of waiting until we have the best conditions. We also have to be in for winds, not a lot of winds to make the rocket go off track. And then we're also monitoring down here on the smaller screen the instruments. So we have all of the instrument currents and voltages, making sure we're getting data streams in from every single instrument so that we know that it's all going to work when we launch it together. And then finally, if this video will play.
3, 2, 1, start, 0.
We launched the rockets. So this was the first rocket. It launched right into the clouds from the vantage point of Poker Flat, Alaska, but it was clear at Venati, Alaska, which was what was really important so that we could get all of our ground-based data together. And you can see that from the pictures here. We can see Aurora from Venati and from other locations like Tulik. We just had to make sure that we had all of the right conditions and then launched right into the fast pulsating aurora for this first rocket. And then, so that night we had, thanks to our engineers, we had a data stream coming in of all of the particles collected that we could see on the screen as the rocket was in the sky. And then right afterwards, we were able to make these plots of the electron spectra from our various instrument. So here we have just what we've pulled together so far is the APES data. So this is the first instrument that I was talking about. So on the bottom here, we have seconds since launch. So I start at about a little over 100 seconds after launch is when the instrument turns on. And then we capture every millisecond a full electron spectrum from 1 keV to 30 or even a slightly higher keV. And this is summed every 10 instrument samples. So this is every 10th of a second, I plot a vertical line. And we can see all of the auroral data that we were able to collect from this mission. It was super successful. This is, again, the first rocket that we launched into the fast pulsating aurora. And we're super confident that we see these structures where it looks like things turn on and then turn off and then turn on and then turn off, which we're sure is the pulsating aurora. And we think we see some fast pulsating aurora too. But there are all these really interesting features of active aurora that you see when you go through arcs and different types of active aurora at different energies. So there's a lot to analyze here. And then just zooming into some of the pieces of that plot that I was just showing. So this is actually, this feature, you can see the spin modulation of the rocket. So the rocket was spinning, I think it was a little over once per second, or maybe a little less than once per second. But so these little pulsations you see here aren't actually the fast pulsating aurora. This is the rocket spinning, and we can see that in our instrument. From when you just get a little bit off of the pointing towards the magnetic field with the instrument, it's an interesting thing that you can see there. But then we do see, zooming in here at the top of that plot on the left, we do see these pulsations going in and out, in and out, in and out, and then maybe even some smaller ones a little bit faster, where we see the fast pulsating aurora. And then on the right is a zoom in towards the end of the flight. And this is actually the individual samples from the rocket. So this is not integrated. This is once per millisecond. And you can see just these different auroral features, super intense, some slightly lower energy. And so it's interesting seeing these discrete auroral features that we want to look into more. And we'll get some analysis going on all of these different things that we see. And then finally, this is the other apes on the other rocket. So this is the second rocket that we launched. Unfortunately, we didn't have the greatest weather conditions or the greatest aurora conditions during our launch window in Alaska. So we ended up launching this rocket through an active auroral arc, but we're not confident that we saw any flickering aurora within this data. But we do still get, and this is the same thing integrated to once every 10th of a second counts. We see lots of active aurora that we pass through, and we'll be able to analyze some interesting features as well. And then here's what we saw from the ground on that night. Here's just another example of these domes that we have of these small cameras pointing at the sky. I believe this one is from Venati, Alaska, but I'm not totally sure. So if someone wants to correct me on that, feel free. But then on the right here, we have a video of our all-sky camera from Venati, Alaska, and this is at the apogee of the flight. So I think this is like 12 seconds long, but and then sped up by 10 times. But you can see definitely, and this is from the first flight again, so you can see definitely these pulsating patches in the middle of the field of view where the rocket would have passed through. And then also just some really beautiful auroral structures going through the field of view, so I'll play that again because I think it's really cool. So yeah, we'll eventually go through and look at the electron spectras and compare that to the intensity going through the optical fields of view. We also have some cameras that are narrow field, so it really points into these small patches with really high resolution of pulsating aurora. And then here's post-launch. So after the rocket flies, it lands somewhere in northern Alaska. You can see the back of this rocket landed right into the snow. They get a helicopter to go out and take pictures and survey everything right after the rocket launches. And then about 4 months later, we went back or the team from Poker Flat went back and collected our instruments and tried to gather all of the scraps. So here on the right, the very right hand of this image, you can see apes, which I think is mostly intact, and we could probably launch it again. But then we also have some of our other instruments, and then just the structure of the rocket that you saw a few slides ago, just all mangled. So yeah, that's the whole lifetime of the rocket flight. And then quickly, I wanted to say our next steps, which is one, process all of the data that we have from all of these instruments, and then compare the electron measurements, our fields measurements, which are magnetic and electric fields that we also had on the rocket, and our optical observations all together to compare these features, try to understand maybe what's causing these electrons to happen to create the pulsating aurora, to create the fast pulsating aurora that we see. And we'll be able to draw some conclusions from that. And then the next step is this February, we're planning to launch the Black and Diffuse Aurora Science Surveyor, which is, you can see the logo up in the top right and figure out that acronym. And then this is actually a photo from that Donna Locke submitted to Aurorasaurus of the Black Aurora. And I think it's a really great picture of, you can see those holes in the aurora that is what we call Black Aurora, and that's what we're trying to target with the next mission. And then here's a collage of all of the members of our team that worked on this project, which is super fun. And then we have many more team members. So here's everybody in front of one of the rockets. So yeah, thank you so much.